This section is 10.1, and it concerns gravitation, and in particular, we began with Newton's theory of gravitation, certainly one of the highlights of his career and one of the most famous aspects of what Newton did as a scientist. Every school child is familiar with the image of Newton presumably sitting under an apple tree with an apple falling on his head when he begins to realize that gravity is universal and may be not just pertaining to the Earth, but pertain to all the planets, the sun, the stars, and so forth. So what is Newton's law of gravitation? It's basically that every mass in the universe, mass m1, attracts every other mass, m2, with a force that depends upon the distance between the two objects, inversely as its square, and is in the product of those two. Now, this force is always attractive, as opposed to the electrical force, which can be attractive or repulsive. And it is along the lines of their centers. The form that this force takes is that the force that object 1 exerts on object 2 is equal to the negative of the universal gravitational constant we'll talk about in just a minute, times the first mass times the second, divided by the distance between them squared, r2 minus r1. And this force is a vector. And the force that object 2 feels is actually going to be in the direction, this is a square here, and the direction is actually going to be as a unit vector r2 minus r1. This is the force direction divided by the magnitude of r2 minus r1. This is this object right here is actually a unit vector which pulls on object 2 because we're writing here the force that 1 exerts onto. So this is the force that object 2 feels. And you can see that if we had a coordinate system here so that r was equal to r2 minus r1 would in fact be in this direction. I believe I have the signs on that correct. I'll check on that in a minute. The first to measure this constant was Cavendish. Cavendish lived from 1731 to 1810, and he measured this constant using a system that was very ingenious. He took a globe of glass, and inside that globe he had 2 small masses balanced, and then 2 larger masses that he could adjust. The small masses were hanging by a fine wire and had a mirror on the front, and he could shine a light in and look at the reflection of that light. And of course, since the light would move with the slightest movement of these 2 masses, because the mirror was mounted on this wire, here's the wire going up to the top of that glass globe, and he evacuated this so it had no air in it, or a near vacuum. So as the light came in, it would reflect on the wire and come over here on the wall, and he had the wire, the wall marked off, and he could look at this angle of deflection. Then these other 2 masses, he was able to take and turn them so that they became closer or further away from the first 2 masses. And in the process of doing that, of course, he could say, when these 2 masses are close, we get this much deflection. When they're further away, we get this much deflection. And he was actually able to measure those distances. Of course, he used 2 masses because then that balanced this whole system so that you didn't have strange torques pulling the thing to the side. He obtained the result that the gravitational constant was 6.673 times 10 to the minus 11th. And that's going to be in units. That would be naturally inverse kilogram squared times meter squared. But this is dimensionless out here, this unit vector, which just points in the right direction. If we look at gravity near the surface of a planet, and let's ignore this for the time being, because we can instinctively know what the direction of that force is, then we've already had the force near the surface of a planet was equal to m times g. And of course it's downward. We know what that is, and we know what g is, the acceleration due to gravity, at either 9.8 meters per second squared or 32 feet per second squared. And I'm sorry, 9.8. And this, we usually approximate this with 10. So this is called the acceleration due to gravity, g. And how can we reconcile these two formulas? Well, if we look at the Earth, which has a radius r, a mass m, and look at an object that's near the surface of the Earth, then we can apply this formula here. And what we would get is F, the force on mass m1, would be equal to g, and I'm going to ignore the signs now, g times m1 times the mass of the Earth. Let's just call it m. Force on m times capital M divided by the radius of the Earth squared. Now, why is that? Because as we vary this only a few feet, that's negligible in comparison with the radius of the Earth, which is 4,000 miles. So if we're within some reasonable distance from the surface of the Earth, the distance we have here is negligible in changing this r squared. And so we just have the radius of the Earth squared. Now we can pull this factor m out front, and what we get is m times g m over r squared. And now if we compare that force to m times g, we see the astounding result that's listed right here in your equations, that g, the acceleration due to gravity, is capital G, capital M, divided by r squared. This, and this, the law of gravitation, and its approximation on the surface of the Earth, here, are extremely important equations. In fact, you can use this equation here to figure out what the acceleration due to gravity would be if you were on another planet. You just take the universal gravitational constant times the mass of that planet divided by the square of its radius, and you can compute g. One problem that's often given that I particularly like is, let's imagine you have another planet, and it has this is of course for the Earth. And now what we want to do is we want to say, what is it for another planet? Let's assume that this other planet has a mass which is equal to the mass of the other planet, which is equal to 8 times the mass of the Earth. And let's assume that the radius of the other planet is equal to 10 times the radius of the Earth. So this would be a huge planet with only just a much less dense planet with only 8 times the mass but 10 times the radius. Of course, as you know, the volume would go as the cube of the radius, so this is going to be very lacking in density, so it's probably going to have a low g. What would we have then? Well, what we can do is we can say g on this other planet is going to be equal to capital G times the mass of the other planet divided by the radius squared of the other planet. That's equal to G, 8 masses of the Earth divided by 10 radius of the Earth quantity squared. Well, we can simplify that very quickly and write that as G times the mass of the Earth divided by radius of the Earth squared times 8 over 100. Because this 10 is squared, that will give us 8 over 100. Well, we know what this is right here. It's G. So this is 0.08, 8/100ths of the acceleration here on the Earth for G on this other planet. So it's very easy, if we know the ratio of the mass of the other planet to the mass of the Earth and the radius of the other planet to the radius of the Earth, to figure out what G would be at that place. Therefore, we can look and easily compute what G would be if we know the mass for an asteroid or for the moon or for any other place that we might be interested in. So again, if you look at this, you can see that this is a very, very small force. I think maybe another problem would be very useful there that I sometimes give, and that's just the force between two people. Many of you have felt attracted to another person. Let's see if that attraction is gravitational. Let's take a force between two people. Let's draw our two people here. And let's make this a male at 100 kilograms, it's 220 pounds, and a female at 50 kilograms. That'd be 110 pounds. I'll give her address. Okay, now we want to put these two at about arm's length apart, which is about 1 meter, and let's compute the gravitational force that's between them. As we compute that gravitational force, it's going to be G, which is 6.67, we can ignore the 3, e to the minus 11th, times the mass of the first, which is 100, times the mass of the second, 50, divided by the distance between them squared. So that's going to be 5,000 times 6.67 e to the minus 11. Well, about what is that going to be? Roughly, even if we round this up to, say, 7, 5 times 7 would be 35. At 3.5, roughly speaking, it'd probably be closer to like 3.3. You can work it out with your calculator. Say 3.3, and I would have 3 decimal places here, and one more because I would get 5 times 7 is 35, and I've moved that, or 33, I've moved the decimal point over 1 there. So that's 4, that's 3, that's 4 decimal places, so that would be E, and now I'm going to have to, that would multiply by the e to the minus 11. That'd be e to the minus 7, 8, 9, 10, 11. I believe that's correct. I always check my algebra. That's 3 times 1/10 millionth of a Newton. Well, just to remind ourselves of what a Newton is, let's see what that force would be. 3/10 millionths of a Newton. Well, let's take a bottle of water. 1 liter of water. 1 liter of water weighs about 1 kilogram. And let's see what the gravitational force of 1 liter of water is. Remember, it's mg. So it's going to be 1 kilogram times 10. So this is 10 by comparison with 3/10 millionths. And that's just for a liter of water. So you can see by comparison here that the gravitational force is extremely weak. It's the weakest force we have. And in comparison with the strong force, you recall that it's about 10 to the minus 39th in comparison with 1, or the strong force, or the nuclear force, and about 10 to the minus 2 for the electromagnetic. This is gravitational. So the gravitational force is incredibly weak. And the critical equations here, of course, the force due to gravity on the surface of the Earth, which we've already covered. The acceleration due to gravity, which we can derive from this equation. And that's true not just on the Earth, but any planet. And it's kind of interesting to remember that this is about 10 in the MKS units. That's capital G, which you know, mass of the Earth over the radius of the Earth squared, if you put those in kilograms and meters. And of course, the most critical one is the core equation for the force that's gravitational. be sure to check the directions on that.